right, test. Oh, yep, perfect. Turn that down. Awesome. All right, hey everybody. Welcome to Dead Week. It's Monday. We've just got 4 more days left of the week. So today, I hope you guys are all doing well. It's good weather here in Ames again. You just can't complain. I hope wherever you are, you guys are doing great. Today we're just going to be covering final exam content review. We're going to do some Taylor polynomial problems. Basically all the feedback I got from that forum I sent out, people were looking for some Taylor polynomial problems. They were looking for a light review on parameterization, kind of just like what does it mean? What does parameterization mean when we talk about Calc 3? And then I had a lot of requests for difference between Stokes and Green's theorem, and specifically to do some Stokes problems. So we'll have basically the bulk will be a lot of Stokes and Greens, but we're going to start with some polynomials and then we'll finish up with some parameterization. So that's the plan. So I don't have any fun warm-up, sorry, no Kahoot today. But let's talk about Taylor polynomials. In one word, what are Taylor polynomials going to be doing? Can someone say it in the chat? Anybody got any idea? Just one word. You can guess whatever you want. Anybody? Approximation. Gosh, yes, Nathan. Estimation. Yeah, thank you, because yeah. Approximation, estimation, something like that. I'm going to say approximation. You know what? We'll do approximation / estimation. Those are both perfect. They're just approximating or estimating something. So when you see a problem, it's asking for approximation or estimation of something. Second order Taylor polynomial expansion for multivariable functions. Remember, we can do it for one variable function, single variable. But for multivariable functions, remember, it's a pretty simple formula. It's just f a of b plus fx times x minus a. If you remember that from Calc 2, plus fy times y minus b. Okay, plus fxx, well, and then plus 1/2 fxx times x minus a squared plus fxy times x minus a y minus b, and then plus fyy y minus b squared. And the trick of these problems is that your f of x and your f of y, your f of xx, your f of xy, and your f of yy, they're all evaluated. Ooh, I cannot spell evaluated. Evaluated at a b. So those are just numbers. Your a and your b, you plug those into your fx, your fy, your fxx, and your fxy, and your fyy. So when we're asked to find the second order Taylor polynomial for this function at 0, 0, what we need to do is find our fx, our fy, our fxy, our fxx. Well, I guess we could start with fxx. And then our fxy and our fyy. We need to find all of those. Then what we need to do is evaluate them at 0, 0. After we evaluate them at 0, 0, then we just basically plug everything into our equation up at the top. Not too much confusion in that, but these problems can get a little trickier. So if we do this, you know, like we would get, if we did the derivative of this guy, we would get 2e to the x plus y, and then it'd be minus, we'd have cosine xy times, and then our inside function, derivative of the inside function with respect to x would be y. And then when we solve it at 0, 0, we're just going to get 2. So our fx is 2, and that's what we plug in up top. So I do this problem out, but I feel like it's pretty straightforward. These are pretty plug and chug problems. Something that we did come up with, your turn with a twist. If you remember this from the exam, I believe this was the fall exam that I'm pulling this from. They gave you the derivative values. So they gave you what those numerical values were, and then they said they wanted you to get the estimate and simplify your answer. So I'm going to see if you guys can do a recall as a little final exam prep. See if you can recall, and I'll zoom up so we can see everything. See if you can solve this problem. Maybe you were able to solve it during the exam, but after a few weeks off of Calc 2 stuff, see if you can solve it. I'll give you guys like 2 minutes. We'll see how well you do, and then I'll help walk you through it just in case you couldn't remember or you couldn't do an exam or whatever. And then yeah, we'll go from there. So time to cue your favorite Spotify playlist for about 2 minutes. Good luck. All right, so let's see how you guys did. Given a little bit of background and having gone through this exam, let's check it out. So remember that all you need to do is plug in what they give you for each one. So g of 2, 4 is equal to 2, so we plug in 2 there, plus, so our f of x is just the same as g of x, right? And it's at 2, 4, it is negative 1. So we'll put times negative 1. Now x minus a, so our x is just x, and our a is 2, as you can see right there. So with the 2 right there, okay, next we do our f of y. F of y is going to be 1 times y minus b. Our b is 4, you guessed it. My mouse is being weird again. 4, there we go. Plus 1 half, so fxx, now it's just the same pattern. 3, then we'd have x minus 2 squared plus fxy. We'd get negative 2 times x minus 2 times y minus b, which is 4. And then our last one would be plus 2. I guess that it didn't copy over. We'd have an fy here, plus fyy, 1 half, and then it'd be y minus b squared. So we'd have 2 times our y minus 2 over 2 times our y minus b, which is y minus 4 squared. And now to solve this, can anybody say in the chat, what do we do next? Anybody? I know someone knows. Insert x and y and solve. Yeah. So we would just insert our x and our y. So that'd be our x, that'd be our y, and then that would be our solution. So then we would say g of 2.2 comma 3.9 is about equal to 2 plus negative 1 times, so for our x we'd plug in 2.2 and then be minus 2 plus, and then for our y we'd plug 1 times y minus 4 would be, so our y is 3.9 minus 4, and we would do that for the whole thing, and then we'd solve that out. And I will spare you the dramatics. That's about as far as we would go. So let's Taylor polynomial expansions, kind of just a quick review. Are there any questions that you guys have about that? Awesome. No questions? No questions? Sweet. I know it can take a second to chat. Oh, so the answer, you know what? I do not even have the answer written down because I was just going to solve it out, but I don't want to waste the time. You could, if you find it, that's on Math 265, spring 20. Spring 20, problem 6. You'll be able to find it. Yes. All right, cool. All right, Green or Stokes. Okay, this is the money making round right here. Okay, so the first thing disclaimer I'll give you guys is I go through, like when I prep these sessions, I always just go through all of the exams just to see what kind of questions they're asking for in the final exam. Granted, this is going to be a little different this year, but on every final, as far as you can go back, there's either one Green's problem, one Stokes problem, or one divergence problem. That's usually how it works out. Sometimes there's been a Green and a divergence, but I've never seen a Stokes and a divergence. But there's always a pretty good chance of either a Green's or a Stokes problem. And I know a lot of people are concerned with basically determining between a Green and a Stokes problem. So we'll do a fun little activity here. I'll let you guys try to do this yourselves. See if you can figure out whether you're going to use Green or Stokes for each of these 4 problems. And we'll see how you do. I'll just sit here quietly for, let's say, like 30 seconds. And see if you can get, it's just 4. You'll have Green, so whatever you think it is. So go ahead and reason that out for yourself. All right, so if you guys have a few answers in your head, we'll go through it with you. I'll just let you say it out loud to yourself. The first one is going to be yes. If you said Stokes, you were correct. Why Stokes? Well, we're looking at 3 dimensions, so that's a pretty big giveaway. You can also see the really big giveaway is the del cross f. They give it to you. That's a keynote of Stokes theorem. Let's look at the next one. Let C be the boundary of the portion. So on and so forth. Oriented clockwise when viewed from the right. See below, there's an image that comes with it. But this is the big one they give you right here. So I'll also let you say it out loud to yourself in 3, 2, 1. Yes, if you said Stokes, you are correct. Congratulations. It might be a Green's theorem problem, and I can see why that'd be tricky. The giveaway for me would be the fact that it's 3 dimensions. But another giveaway is it's a function dot t. If you see the dot t, remember the equation for Stokes theorem says that if you have basically like something like this, if you have f dot t ds, that is what Stokes theorem is. Sometimes they tell you to do the curl. Sometimes they don't. Oh, I guess it'd be curl dot normal vector. But the big thing is that right there is on the left-hand side is a Stokes problem. Okay, cool. Also, the 3 dimensions give it away. Let's look at the next one. I'll let you say it out loud to yourselves. See what you got in 3, 2, 1. Yes, Stokes theorem. The giveaway is good right there. Easy, easy money. They already give you the equation for Stokes theorem, which is perfect. All right, cool. Let's look at the last one. I bet you can guess it. It's going to be, yes, Green's theorem. We see 2 dimensions, and we see an m dx plus an n dy. So because we see both of those things, that's definitely going to be a Green's theorem problem. I mean, they even give you it in the Green's theorem form, so that's pretty good. Okay, cool. So that's kind of how we would figure that out. So let's talk about what those are exactly. Well, I guess first, are there any questions on identification? And we're going to do even more problems, so you'll even get more familiar with identification in a second here. All right, cool. So let's talk about Green's theorem and Stokes theorem. Just a quick refresher. So we have, remember, m dx plus n dy. That would be, so we have that. What you can say is that's the same thing as if we do a double integral of the region, dA, and if we have nx minus my. So that is Green's theorem. Stokes theorem, remember we kind of went through this, the f dot t ds over a closed surface. Remember both of these are closed surfaces. Then we'd have a double integral of the surface. We'd have the del cross f, or the curl, dotted with the normal vector dsa. Those are the 2 big ones. And it's abstract. I hate looking at these equations because it's really hard to understand what they mean. So what we can do is let's look at some examples here. So let's try this one. Evaluate this function where c is the circle, x squared plus y squared is equal to 1, traverse clockwise. So I'll pull this up so it's a little bit better. There we go. I don't think I have it. Yep, I just have 2. So you see we have an m dx plus an n dy. Is this Green's theorem or Stokes theorem? Anybody tell me? Greens, yeah, exactly, greens. Because it's 2 dimensions, and we have an m dx and an n dy, just like we saw above. So we know that the integral of the m dx plus the n dy, that's the same thing as we have the double integral of n of y, or n of x, excuse me, minus m of y dA for the region. So I'm going to let you guys try to solve this right away. Find your n of x, find your m of y, set up your integral, and see if you can solve that. I promise you it's not as hard as you might think it might be. I'll give you, let's say, 3 minutes, and we'll see how well you guys do. Good luck. All right, so let's see how you guys are doing. Did anybody get 4 pi? Question mark? Anybody? Anybody out there? Nice. Okay, nice job, Nathan. Nathan got 4 pi. Awesome. So if we look at it, yeah, okay, sweet. Everyone's getting 4 pi, man. So if you got your nx, you got 7. Your my, you got 3. So now you just have 7 minus 3 dA, and then it's your region. So you have 4 times double integral dA, and your region is just a circle with radius 1. So that means your area is pi r squared. So it'd be 4 times pi r squared, and your radius is 1. So if your radius is 1, then you'd have 4 pi is your answer. Awesome. Nice job, everybody. Sweet. So let's look at another one that is kind of related, but maybe not too far related. Okay, so is this problem Green or Stokes? Let C be the boundary of the portion of the cone, oriented clockwise and viewed from below, and you can see we have something dot T. It is Stokes, yes. I could hear you all screaming it inside your head, just wanting to come out so badly. So we have a Stokes problem. So let's see. So remember the Stokes equation. I guess we can write it down really fast. That way we're all on the same page. Dot T ds. Wow, that's a bad T. I'm gonna get rid of that. F dot T ds. So it's equal to the region, right? If we across the region, or I guess it's technically across the surface of del cross F dot N dsa. The only change I didn't put a surface is just because of the dsa. Okay, sweet. So we have the Stokes equation, we have the Stokes problem. So let's look at this. Figure out your normal, find your del cross F, and be smart about it. So remember that you only need the component from your del cross F that your normal is going to. Your normal is going to have 2 zero components. So if we look at it, and we can all look at this together to figure out what our normal is. Something they've never said in the lecture, so don't like quote me on this. But you can figure out the normal if it's a surface with a direction like that from the right-hand rule. And it's always worked for me. Where if you curl your hand, I don't know if you guys can. I wish I was in session because I could do this. But if you take your fingers and you send them along the curl and put the palm facing towards the inside of the curve, and then curl your fingers around the curve, whichever direction your thumb is sticking is the direction of your normal. So our normal is going to the left like this. And of course we have a graph that's like an x and a y and a z. So our normal vector is, oh, okay, perfect. So I can now quote it. So if we have, using a right-hand rule, we'll have 0, and then we'll have our y component, and then we'll have our 0. Of course, they don't really give you like units on this graph, so it'd be kind of hard to interpret. And if you're on the exam, it'd definitely be worth a question, but it's a -1. It's in the negative y direction, technically. So we have our direction. Find del cross F. Be smart about it. I'll let you guys try this out because we've done problems like this a lot. And then see if you can compute your integral. I'll let you guys run this for let's say 4 minutes, and then we'll see how well you guys do. Cue your Spotify playlist. I believe in you. right, we'll see how everyone's doing. Has anyone gotten an answer yet? Anybody? 100 pi. Oh, we've got an answer. Okay, 100 pi. Anybody else? Nathan, you were close, but no cigar on that one. Okay, well, I'll give you guys, let's go through the first few steps, and maybe I'll let you guys work this one out to completion. This is kind of a fun one to do. So if we do our cross product, and I'll do it up here, just so I don't have to scroll down the page and we're crossing our eyes to see the whole thing. I, J, and K, and maybe I'll need a little more room. J, K. So our I is going to be the sign. Well, then this would be partial x, partial y, partial z. And then if we're going to have the sign of x cubed minus y plus 2z. And then our next one is, oh my gosh, arctan of x, y, z. Don't worry, that one doesn't matter anyways. And then the last one is 4x minus yz squared. Okay, so we have our cross product. But remember, our normal is all we want is the y component. So when we do our cross product, we can be a little smart about this. We can say that is equal to, we'll have remember, I kind of do the cross product one way. I compute my I, then my j, and then my k. Certain people have it certain ways, but we have our I, but we don't care what's in there because it's just going to multiply to a 0 when we use Stokes' theorem. So we don't care what that I component is, minus the j. The j is the one that we do care about. So let's do the j one. And then I do the j one where, like I look down the j, so then I cross that off, and then I cross that off, and then I take the determinant of whatever's left. So I take the determinant of there. So it'd be partial x times 4x minus yz squared. The partial x of that is just 4. And then minus, and then we go the other way, right? And then I take the determinant that way, and I'll get rid of all that so it's not as nasty. Get rid of all, there we go. So it'd be 4 minus, so partial z times the sign of x cubed minus y plus 2z, so there's just a 2. And then we'd have plus k times, I don't care because it's going to be multiplied by 0. So then our del cross f is equal to, like something, -2, and then something. Okay, so we did our cross product, we find our del cross f, and now we can compute the integral. So I'm just gonna kind of cross this out because we found the del cross f. And now let's just compute the integral up here because we have some room. So our integral, double integral of the region, I guess technically the surface, I'll write an h again. So we have our del cross f dot n dsa, and we sub everything in. So we'll have a region, and we'll save the bounds for that. I guess we could do this. And then we'll do, our del cross f was something, -2, something, dot, not times, dot, 0, -1, 0, dsa. So with the dot product, remember we just multiply each component. I'll make this pretty. Maybe I'll do different colors. Go there, and then we'll do there. And all that leaves with is the middle term, so it'd be -2 times -1, so it'd be a 2 of our surface dsa. So now we need to compute that integral. I'll let you guys look at it for let's say 1 more minute. See if you can figure that out. I believe that you can. It's just a little bit of geometry. Sorry, it's going to be a little small on your screen, just so I can get everything in there. 50 pi. I see a 50 pi in the private chat from Anonymous. Let's see if we get anything else. All right, so if you got 50 pi, you were correct. And here's why. Let's look at it together. So we have, basically, we want the area of our surface area of our surface. And our surface is this circle that we're using, right? That's what we're circling about. So if that's our surface, we need to find the area of that surface. So we need to know the radius, and then it's pi r squared, easy. So the radius, remember that our whole cone is described by that equation up at the top. Y is equal to the square root of x squared plus z squared minus 3. And our circle exists at y is equal to 2. That's the y coordinate our circle exists on. So it'd be 2 is equal to the square root of x squared plus z squared minus 3. If we bring that c to the other side, we get 5 is equal to x squared plus z squared, or 5 squared is equal to square. Well, I guess we get rid of the square root, x squared plus z squared. So 5 squared, that's a radius, right? 5. So we have a radius of 5. So with a radius of 5, our surface area is just going to be pi times 5 squared times the 2 that we already have, which is 50 pi. So that would be the final answer. Not much Stokes in that, just a little bit of geometry. But yes. Awesome. All right, let's move on to the next one. So, is this a Green's or a Stokes problem? Why is the 2 not used? Oh, yeah, of course. So, because I asked, why is the 2 not used and not the negative 3? So, right here is y is equal to 2. Down here, this is y is equal to negative 3. Because this is the y-axis. So then this would be like negative 2, 1. Yeah. Yeah, right? A little light bulb there. Awesome. All right, cool. Are there any more questions? Awesome. All right, cool. We'll move on. So let's look at this one. You already had a sneak peek at it. You had time to think about it. Is this one going to be Green's or Stokes? You tell me. Yes, it is Green. We have an answer. Yes, it's Green's theorem. Why? Because, I mean, most of the biggest giveaway is 2D. I would say because it's 2D. Also, it's got the m dx plus the n dy kind of deal going on. So we've got Green's theorem. Remember, that is equal to the region, if it's n x minus my dA. So let's see how well you guys do on this one. I believe in you guys. I'll let you run on it. I think you could do it. The hardest part is going to be setting up the bounds, I think. And setting up the bounds isn't too bad. You make sure you use dx dy so we all get the same answer. And yeah, I'll let you guys run for, let's say, maybe 2 minutes on this. You don't need to compute the integral. That involves a little bit of a u-sub and kind of nasty math. We're just going to set up the integral because I believe you guys can solve the integral, at least on your own time during the final. So yes. All right. Start your playlist. I'll give you guys 2 minutes. Good luck. All right, let's see how you guys did. So setting up the integral, we need nx. So if we take the derivative of our n with respect to x, we will get y cosine of y squared minus 1/3 y cubed. And if we take it with respect to m with respect to y, ooh, my handwriting is going down as the semester goes on. My, we get a nice big fat 0 because there's no y's in our m, which is perfect. So now we set up our Green's theorem equation. We are, and maybe I'll leave that because we'll write our bounds soon. Y cosine of y squared minus 1/3 y cubed. And we said use dx dy, so we all have the same answers. So this goes way back to writing bounds in 2D for multivariables. Man, remember when we just got first introduced to multivariable integration? And now we've just been doing it forever and we're so good at it. So let's start with our y, right? The outside bound has to be a number. There can be no variables in the outside bound. So let's start with our y. Our y, we go from 0 to 2. And now let's look at our x. So we're slicing the x on the inside, which means we're moving like this, right? So if we move like that, our left-hand side, which is the bottom of the integral, is going to be x is equal to y. Yes. Okay, and how about our top? I'll let you say it to yourselves. X is going to be equal to, yes, 2. You said 2, you got it right. Sweet. So now we set up an integral. And we could solve that if we wanted to, but this is all I was asking for here because we got 7 minutes left and we really got to get moving. So, yes. Are there any questions about that one? Nice little Green's theorem problem. The hardest part is that is going to be solving that integral for sure. Awesome. All right, let's press on. So, I think I had another problem here. Yes. We've seen this one actually. If you want to see this, go back to some of our old lecture stuff or our old SI session stuff. You can see us solve this one. But yeah, let's talk parameterization really quick. So how would you solve this problem? Remember that work is equal to the integral of f dot dr, if you remember that, which is kind of weird, kind of not weird. But we can take that and we can convert it. Remember, it's a line integral technically, but it's not a closed line integral. So remember, if we have the circle on there, we could use Green's theorem because it's closed. But because it's not closed, we can't. Which means it's going to be equal to m dx plus n dy, but it's not equal to nx minus my. We cannot use that. So we have to solve it just like this because it's not a closed integral. If it were closed, we could, but it's not. So how would we solve this? So we've got our m dx and n dy, but we've got some t's in there, some parameterization. So if you guys remember this, we went over some of these problems a while ago. What you would have to do is first of all plug in your m and your n, and your m and your n come from here, right? There's your m, and there's your n. So you would plug that into your equation. It would be x plus y dx plus, okay, our n is xy dy. And now how do we solve from here? Well, we are going along the line from 0 to 2. And they give us the parameterization of the curve as x is equal to 2t and y is equal to t squared minus 1. So they give us a parameterization and they give us how far we can go. So what we can do is convert this integral. We can set the bounds from 0 to 2. T is equal to 0. T is equal to 2. And we can plug in a t for everywhere there's an x and a y. So then we plug in, for x, we plug in 2t, as you can see from above. And then for our y, we plug in t squared minus 1. And I think we went over this exact problem earlier, if you guys were tracking our sessions earlier in the semester. And then for our dx, all we have to do is take our x and take the derivative with respect to t. It'd just be 2. And for our dy, it'd be 2t. And then we would just plug that in, literally plug that in for dx. So then we do it times 2. Plus, and the same thing goes for the xy. It'd be the same thing all the way down. So that's how we would solve a problem like that. And we can go on and, because we only have just a few minutes, I'd like to just talk about parameterization. So what about this problem? Because there's a lot of lines on here, and I don't want to have to set up like what is that, 1, 2, 3, 4, 5, 6 integrals. If you remember, there was something we talked about conservative. So conservative is when m of y is equal to n of x. Do you guys remember that? I believe it's m of y is equal to n of x, yes. And if you have that, then what you can use is the potential function. You guys remember the potential function, f of b minus f of a. You can say it doesn't matter what path I take when I get to the finish. If I start at if I start at a and I go to b, if the function is conservative, it doesn't matter which path I take. Going from a to b, it's going to be the same exact thing when I subtract the potential functions. So that's how you would solve a conservative problem. So if you see something nasty like this where it's got a nasty path, see if it's conservative or not. If it's conservative, then you can just basically find the potential function. If you guys remember finding the potential function, this is where we had to take like the integral. We kind of had to do like a reverse partial derivative where like f is equal to 2x minus y e to the xy. So this is our function. I'm just copying it from above. And what we have to do is kind of take like we have to understand that this is f of x, right? This is f of y, and now what we need to do is take like the reverse partial derivative. So it'd be like almost be taking like the integral. So this would turn into x squared minus e to the xy, because if we took the derivative of this with respect to x, it would bring us right back to where we came from. And then for the other one, it would be just negative e to the xy, and those kind of match up. So then our potential function is kind of what those two combine from. It'd be x squared minus e to the xy.